All right, we will introduce calculus, what you're going to learn. We will introduce the building block of calculus, which is limits today. Calculus is the mathematics of change, or the math of infinitesimals. It was discovered in the 1600s separately by both Isaac Newton, the father of physics, and this guy called Leibniz. And they both discovered it right around the same time, and we don't know who discovered it first, which is interesting. It was in the 1600s. And there are two major problems that calculus solves. These are the two major problems that we will study, and it'll take us all year to study them. First problem is finding the tangent line anywhere on a curve. So here's a curve. Both curves are the same for both problems. And given some point, say C, what we will be able to do is at the function value above C, we'll be able to find the slope of this tangent line, and we'll be able to generate this tangent line, just like a normal tangent line that you're used to in geometry, you know, of a circle. It's just touching the circle once. It's technically kind of touching the function once. We'll see in the future how that's not always the case. But we'll also see that finding this tangent slope is finding the instantaneous rate of change of the function. Please stop me if you can't read, of course. Rate of change. To do this, to find the slope at this point, we will take 2 points on the function that are infinitely close to each other. We're going to use a simple slope formula to find the slope at that spot. However, you guys aren't used to this infinitely close thing, and that's where calculus comes into play. Okay? We will use notation that will look like this. It's going to seem very foreign to you now, but it will be very familiar to you eventually. You will take the derivative of the function at the specific value. This is called differential calculus. And throughout the entire first semester, we will study this. That's an R. Second question that calculus helped solve was finding the area, an exact area, or an exact volume of an irregular shape. So take the same function. What we're going to do is take two kind of boundaries, starting at A, going to B. And we will calculate the exact area underneath that function above that x-axis. To do this, we are going to slice this into infinitely many rectangles that are infinitely skinny, and we will sum that infinite amount of rectangles together to give us an exact amount. Seems crazy, I know, but don't worry, you'll do it. The notation for this is this S. It's kind of a skinny capital S. Stands for an infinite sum. Starting at A, going to B, of all of these rectangles that are going to have height of f of x, or function values, they'll have widths of dx, which is just notation for an infinitely skinny width. This is called integral calculus. You'll do this in the second semester. And that's it. That's all we're going to learn. But we're going to learn applications of both things. We're going to learn that over here we can use our tangent knowledge to find maximums and minimums of different functions. We'll be able to find tangents of tangents, and then it'll tell us about how our function reacts and how it looks. Over here, we'll take this area, we'll spin it around this x-axis, making a three-dimensional shape, and we'll be able to find the volume of that shape. Turns out these two are very related. It's kind of going one way for the first question, it's going the other way for the second question, which you'll see is interesting. But before we tackle those problems, we need the building block of calculus, which is limits. We will define limits in a second. So maybe just write it down or hold it off. And before we define limits, we're going to review function notation. So given a graph, getting information from our graph. So go ahead and copy down this example. This is a good example to have. We'll use it a couple times. So it's a coordinate plane. It's a function. We can label it f of x. We have an x-axis. And you're familiar with this being the y-axis. However, we kind of move away from y's in this class, and we call them just a function value axis, so an f of x axis. Our x-axis is a great axis. It gives us the inputs. Of what I put into a function or an equation. And the y-axis, the f of x axis, typically gives us our outputs. Now, since f of x is the same as a y, I can ask you a simple question like, what is f of 1 equal to? Mr. Magnella, what's f of 1 equal to? That's correct. We go to an input of 1. Here's my input. My output, or my function value, is 2. So Ms. Gross, what's f of 4? Exactly. Simple. This being my x is my input. This being my y, or my function value, is my output. All right, now the question, Miss, not Gibbons, it's Golden. Miss Golden is, what is f of 3? Yeah, we think it's -1, right? Why do you say -1? Yeah, because at 3 we see -1. However, that's not the case. We have an open circle here. I set you up, but you gave me the right answer. Don't worry, we're going to come back to you. We have a case where we have an open circle. An open circle signifies that there actually isn't a function value there. There's a hole. There's something missing. So turns out f of 3 is not 1. It's undefined. But what I could do is maybe put a closed circle above it if I wanted to. And all of a sudden, this f of 3 that was undefined is now defined as 1. Okay, so if it's without the red dot, we would say f of 3 was undefined. We have an open circle at 3. There are no function values there. But with the red dot, f of 3 is now defined. Okay? But I like what you said, Ms. Golden, about it being -1, because that's kind of what we're going to talk about next. Here's the definition of a limit. The limit, or a limit, is the value that a function approaches as the input approaches some value. So using this same example, I can say, well, I know f of 3 is undefined. There is no value. There's an open circle at 3. But, Ms. Golden, what does it look like our function could be? Or what does our function approach as we get close to 3? -1. You just kind of found the limit. The function f of x approaches or gets really close to -1, that's the function value, as the input for x gets close to 3. Okay, so it's just kind of like, where is the location of this missing piece? Well, as I approach 3 on my input, for my inputs, my function values move down and they approach this value here at -1. I can go from the right as well. As I approach 3, my function is approaching -1. Cool. That brings us to limit notation, not having to write this statement out all the time. There's shorthand mathematical notation. We say L, undercase LIM, that stands for the limit. And we, underneath the LIM, we do X, an arrow, and a C. Now, it's usually a number, it doesn't have to be a C, so it's the limit as X approaches some number of whatever my function is. It could be an equation in there, it could be f of x, g of x, h of x. That's equal to some other number. We'll signify it by L. This reads, the limit as x approaches c of f of x is L. Now, it's important to know that C and L are numbers, or values. You just use C and L as variables. It could be anything, as long as they're numbers. Okay? So going back up to this example, we stated f of x is approaching -1 as our input is approaching 3. We can now write the limit as x approaches 3, so this is being my input, my x values, of my function, f of x, that's equal to -1. Now, real quickly, what is f of, I don't like that green. Let's look at f of 1 again. Mr. Magnell, what was f of 1? 2. Okay. Now, it's defined at 2. You can think of it as being a closed circle there too. You know, that function is actually a collection of closed circles. It's just an infinite collection of closed circles now put together to look like a line. Okay, they're all just closed circle points. What is the limit of this function as x approaches 1? What do you think, Miss Pennington? What is the limit at 1? So we said the limit as x approaches 3 of this function is -1. What is the limit as x approaches 1? It is 2. So here we had an undefined value, but our limit existed, and it was -1. Here we could have a situation where we just have our function value being the same as the limit. Okay? Limits are not always at crazy spots. They're everywhere. It can be at a function value. It can be anywhere you want to look at. You can look at the function value and you can examine the limit. But technically we weren't really caring about this spot right here. We were caring about the function values to the left and to the right of it. And they turned out to be the same. Might be confusing, but it's not too bad. Let's look at this next example. This is a piecewise function. It's got 2 pieces. We kind of start off down here at -3. We stay at -3. We leave it here, and we get picked up here at -2, and it goes up there. What could we say the limit as x approaches 1 is in this situation? So as my input approaches 1, what could we say our limit is? Mr. Wenzel, what do you think? Yeah, maybe it's -2. Because you see this closed circle here, so maybe like -2 looks like a great answer. Well, do we see another possibility that it could be? Mr. Sargent, what do you think? Could be undefined? Why do you say undefined? Okay, well, we know what the function value is. How about we start with that? What's f of 1? Is it undefined or is it a value? It's -2, exactly. So the value is -2 because you got the closed circle. But you were right, Mr. Sargent. We got this -3 down here, and it looks like we are approaching this value, and we're approaching this value. So maybe it's -3, maybe it's undefined. I'm not sure. We're going to examine this, but we need to introduce something called a one-sided limit. One-sided limits are there so that you can look at a specific area as we're approaching. We can look at a specific side of the input value that we're focusing on. So the notation changes a little bit. It's the same undercase LIM, X arrow as X approaches C, but you're going to put a negative sign like in the exponent of the C. Okay? This negative says that we are going to look at inputs to the left of C. Or some values for our inputs that are less than C. If we think about to the left of 1, we're looking at numbers less than 1 over here to the left of it. This is called a left-hand limit. Or LHL for short. Nice job, Mr. Bolner. Now, let's look back up here. What do I mean by left-hand limit? I can, instead of looking at 1 in general, because we're kind of confused about 1, I see -2, I see -3, maybe it's undefined. I'm just going to change it up. I'm going to say, let's look at 1 from the left. What I do is I look at my input 1, and I'm looking just a little bit to the left of 1. So input's a little bit smaller than 1. And I'm going to look at my function value, what my function values are approaching as we get closer to 1 on my input from the left. Mr. Satterfield, what are we approaching as I get closer to 1 from the left for my function values?
Wouldn't it be still negative?
It would be -3. Interesting. Now, if we have a left-handed limit, we need to have a right-handed limit. The notation is almost the same, except you just have a plus in the exponent instead of a minus. It does not mean -1. Like if I put this negative here, this is not -1. It is 1 from the left. Okay? C with a plus means the number from the right. Inputs to the right. The inputs will be a little bit bigger than the value you're looking at. And we call it the right-hand limit, or the right-handed limit, or RHL for short. Okay. So we looked at the left for this example. Let's look at the right. Limit as x approaches 1 plus. Miss Highland, what do you think this limit as we approach 1 from the right is? -2 is correct. As I'm looking at inputs to the right of 1, I see that my function values, as I get closer to the input of 1, those function values are getting closer to -2. Okay? So we have different left-hand and right-hand limits. Question, Mr. Magnella.
Are these only for equal functions, or can they be used for sine?
So sine and cosine, it can be used for any function, these one-sided limits. But the only time that these limits are going to be different are situations like this, where we have these breaks. Turns out we can look at the left, we can look at the right, and we can look at the limit at 1 in general with no plus or minus. Mr. Sargent, you were pretty much correct when you said that the limit was undefined. Turns out the limit at 1 in general does not exist in this situation. D and E. I'll tell you why. Because for a limit to exist, we'll talk about the existence of limits. Limits only exist when the left-hand limit is the same as the right-hand limit. I'll use math notation. We want to find the limit as x approaches c of a function. If we say that equals L, that's only the case if and only if, that's an IFF, stands for if and only if, the limit from the left is equal to the limit from the right, which is equal to that value you're looking for, the same value. And this is an L, this is a number. If the left-hand limit equals the right-hand limit, the limit exists. And it's whatever those limits are. If the limit from the left and from the right are not the same, then you say the limit does not exist, or you write D and E. That is The limit does not exist. You all remember that from Mean Girls. That's this lesson. Okay? So going back to this example, we can look at the one-sided limit at 3. From the left, I look at my function values. My function values are approaching -1. Let's look at from the right. From the right of 3, here are my function values to the right of 3, or my inputs to the right of 3. My function values are approaching -1 as well. So we were correct in what we said from the start, that the limit as x approaches 3 of this function is -1. Checks out. Okay. Here's a big example. You do not necessarily have to copy it down. There are kind of 4 questions for each location that we're going to focus on. So this is all questions about -4. I want the function value at -4, the limit from the left, the limit from the right, and then you can answer if the limit in general is a value or does not exist. We'll do it for 1. Give me the function value at 1, the limit from the left, from the right, and then tell me if the limit exists, or if it doesn't. If it exists, tell me what it is. We'll do it as well for 6, okay? I want you guys to work on this by yourself. You don't have to copy down the example if you don't want to, but you can just write the answers. And then I want you to check with your neighbors that you've met and you know, and you can help out now, okay? It'll take a couple minutes to do it. Once you're done, look around and ask a friend. See if they got the same thing. This is -4 from the left. All right, see if you can get the answers. Just write them down, maybe like in the corner or something, and then check with a neighbor once you're done. 16 numbers to write down. Or you can write down undefined or something. Or does not exist. That's a possibility. All right, start checking, start asking. Get help from a neighbor if you need. What do you got? What do you think? Well, I don't know. I'm not sure. I think this is this, but what about that? It's okay if you did. You didn't have to, though, but it's all right, Mr. Bowler. How are you doing, Ms. Gross? Good? All right, let's see how we did. F of -4. Miss Alexander, what'd you get for that? So, since it's an open circle, there is no function value at -4. So it's actually undefined. But, Miss Alexander, you're correct for every single question at -4. The function is approaching 2 from the left. It is approaching 2 from the right. And it is approaching 2 in general, since the left-hand limit is equal to the right-hand limit. And that value is 2. Okay, so that open circle, that means it doesn't exist there. There's not a function value there. It's just it's something that you can't even see in your calculator. We'll see in a second when we look at an example in our calculator. It is just a tiniest hole where your input just is not there, and there's no output right there. All right, Mr. Conwell, what do we get for f of 1? 4, and what about the limits?
4, -2,
Perfect. From the left, we are approaching 4. From the right, we are approaching -2. So this limit does not exist. And Mr. Jones, what about 6?
5, 5.
Okay, let's see. So f of 6. I go to input 6. What is my output there? You said it's 5. I see this open circle at 5 saying that there isn't a value there, but there is a value at 6. What is it? That's correct, Ms. Karczewski. Hi.
Hi, I was in your fourth period class today, but I got switched to the second.
Sweet. Fun. Can you come fourth period? No, because you're already switched. Okay.
What about Candace?
So you got those 2 seats there, maybe a seat here. It's up to you. All right, so Mr. Jones, f of 6 is actually 2. This is that red dot there. That signifies the function value. But you were right about the limits. From the left, if I look at values to the left of 6, the function values are approaching 5 from the left. From the right, the function values coming towards 6, a little bit bigger than 6, those function values are approaching 5 as well. Now, Mr. Jones, if the left-hand limit equals the right-hand limit, does the limit at 6 in general exist? Yes. The left-hand limit equals the right-hand limit. The limit exists, and it is at that location. Okay? Now, real quickly, let's look at f of -3. Mr. Rogers? Mr. Rogers, what is f of -3? Looks like 3, right? What about the limit from the left at -3? 3. What about from the right? 3. So the limit at -3 is 3. Everything that deals with -3 is easy because it just has a function value there. And since our graph is continuous, then we know we're going to be approaching this value here at 3. So if I asked you the same questions, but it wasn't at these situations with holes, it should be simple, okay? Any situation where we have just a continuous function with a point, all 4 of these answers will be the same value. In this case, if it was f of -3, all of the answers would be 3. You cool with that? Cool. All right. You might have a question like this on your homework, where it asks, find all values C such that the limit as x approaches C of f of x exists. Okay. The question is, find every possible C where the limit exists. Who's got an idea? This is a volunteer question.
Can you say where it's not?
Yes, Mr. Magnella, that's perfect. If we just say where it's not, that might be easier than trying to say where it exists. And why do you say that, Mr. Magnella? Yeah, there's infinite possibilities. Like, here's a point right here. The function value exists, the limit exists there. Here's a point right here. The limit exists there. There's infinite amount of these points where it exists, but there's just 2 that doesn't. And what are those 2? Ms. Karczewski. 2 and -2. The limit does not exist at -2 because the left-hand limit is -1. The right-hand limit is 3. The limit doesn't exist at 2 because the left-hand limit is 1. The right-hand limit is -2. You would answer this all x's except for -2 and 2. That would be the simple answer. X's that don't equal -2 and 2 are all of the locations where the limit exists. All of these points, everywhere, the limit does exist. It's just at those 2 jumps. Any questions? All right. Now, we can find limits of functions with our calculator. If you have a calculator, break it out. If you don't, you can grab one from my desk. Here's a function f of x. We can write this down. Function values are given by the equation x cubed minus 1 over, or the expression x cubed minus 1 over x minus 1. I plug in inputs for x. They'll give me outputs. We can then plot and graph that function. We're going to focus on 2 limits, the limit as x approaches 1 and the limit as x approaches 2. We're going to see if they exist, and if they exist, where they are. Now, we have our calculators out, so what we could do, and we're comfortable now, hopefully, with questions where I'm looking at the graph of these functions. I can kind of find all these limits. If I want to try to find the limits of this, I could also graph it. You know, your graphing calculator has graphing capabilities. Let's go ahead and graph it. First of all, especially if you have one of my calculators, go ahead and reset it. 2 plus 712. So you have a reset, create calculator, basic settings, because we might change something. Okay, but let's go ahead and turn this equation into something we can visually see. So go into your y equals and let's graph it, see what it looks like. Make sure you use parentheses around the x cubed minus 1 and the x minus 1, or else you will not get a graph that looks like that. Looks like a parabola. All right, I want to find the limit as x approaches 1 and the limit as x approaches 2. Any ideas or suggestions? You guys have used these calculators for a long time. You are experts. You know all the things that you can do with your calculator. So what do we think? Try to find the limit as x approaches 1 and 2. Ideas. Mr. Wenzel, what do you think?
Put it into the y value.
You mean as like an x value, as an input value? Yeah, so maybe we can go and try. I don't know if you can just press a value. No, you have to actually press trace first, and we can see what is the function value when x is 1. Y becomes blank. Why is that? Exactly, Mr. Rogers. I can't plug in and find f of 1. If I do that, I notice I get 1 cubed minus 1 over 1 minus 1, which is 0 over 0. 0 over 0 is indeterminate. You're not allowed to divide by 0, even if you're trying to divide 0 by 0. Or undefined. So f of 1 is undefined. I can't find the value. But I kind of can see where it's supposed to be. If I look at the input of 1, I see, man, the graph is right there. How can I kind of see where that location of that blank missing piece is? Any other ideas? Maybe we look at the table. Let's go to the table. Well, our table goes from 0, 1. It tells us that I don't have a function value at 1. There's that error. And then it goes to 7. So maybe we say, all right, it's somewhere in between. But I need the exact value. So that's good, but not great. Maybe I can use trace. You guys ever go into trace? Depending on how your calculator is set up, some traces go by decimal points. But you can kind of trace to the left on your function and trace to the right and see, hey, if my input's 0.851 this, my output is 2.5. And I can kind of see where my function values are around 1. What do we think, Miss Bench? Where do you think that missing value is around 1? Yeah, it looks to be around 3. Now there's going to be a different way that we can do to confirm this. Pretty much what we're going to do is, instead of plugging in 1 into our equation, I'm going to start plugging in a bunch of values like 0.9, and 0.95, and 0.999. Those values will give me something when I plug it in. So I'm going to just start plugging in random values into this equation that are approaching 1, and that should tell me what my function is approaching. Now, I could do this in my calculator, kind of doing with parentheses divided by this, but it'll take me a long time to enter in all those things. There is a quick and easy method to give your calculator inputs or x's and for them to give you outputs. And I'll show you. I don't think you've learned this yet, but maybe you have. So I want to quickly be able to just plug in like 0.9 and get a value. If you go to trace, you can do this. 0.9, 0.95. You can even see where it's going. 0.999. You're getting closer to 3. 0.9 4 times. Getting closer to 1, approaching 1. My y value, my function value, is getting even closer to 3. That's one way you can do it. A second way, you go into table set. So that's above window. You switch your independent from auto to ask. And if you go to your table, you notice a blank screen. Here, you can plug in values, and your calculator will quickly give you your outputs. So all I'm doing is just saying, all right, you want to figure out what my function's approaching as I get close to 1? We'll plug in values really, really close to 1. That'll tell me what my function's getting close to. I actually like trace better. I used to teach my kids just to do this, but I like trace because you can see it. Okay, but this is telling us that we are approaching 3, just like Miss Bench said. All right, you guys figure out what the limit as x approaches 2 is, and check with a neighbor. Remember, to be able to type in numbers, you have to go to trace. Press trace first, and then you can type in numbers. Check with a neighbor once you get it. All right, Mr. Mozich, what did you get? And how did you get it? Yeah, that's the easiest way to do it. Sure, I can plug in, okay, 1.999 in my trace and see where I'm getting. But Mr. Mozich, you did the right thing. You said, hey, if my function's defined at 2 and we're continuous through 2, it's going to be a piece of cake. I just plug in 2. I find out the function is defined at 2. It's equal to 7. And so that means we must be approaching 7 from the left and the right. Okay? You could have done the process of plugging in 1.9, 1.95, get closer and closer, but is just not necessary in this case because the function value exists. Any questions about that? All right, I want you to evaluate the limits of 1 over x as x approaches 0 with your calculator. Bell's going to ring in 2 minutes. Just hang out. We're going to finish the lecture, and then you guys can use the bathroom, take a break, and start your study hall. Yes. Yep. You can visually look at 1 over x, graph it first. That's your function that we're evaluating. See what it looks like. Like this. Yeah, so it's not defined at 0. If I plug in 0 in for x, I don't get a value. So maybe we need to look at values close to 0 from the left and from the right. Let's see. Type in 0.001. 0.00001. What do we think? Thoughts from the gallery? That's what the function looks like. What's the limit? That's exactly right, Mr. Rogers. If I look at 0 from the right, my function's going all the way up here. What we can say is that this limit from the right of 1 over x is equal to infinity. or it just does not exist in and of itself. A limit has to be equal to a number. So I don't even like infinity, but you can use it. You need to be familiar with it. So we're going up to positive infinity for our function values to the right of 0. If I'm looking to the left of 0, so inputs just to the left, I'm going down continuously. We never meet up anywhere. This is going down to negative infinity. The left-hand limit does not equal the right-hand limit, so the limit does not exist. Now, the reason why I'm crossing out these infinities is because, like, you don't, it's either infinity or does not exist for both of these cases. This one being positive infinity, this one being negative infinity. Go ahead and just put positive infinity, negative. All right, let's pop up here to this one. Absolute x over x. Try that one. And then we got a piecewise example we need to do. And then we'll call it. If you forget how to pull up absolute, it's in math. You go right to number, and then enter on abs. Press right to get out of the absolutes, and you can grab it. Go ahead and check out the limit from the left of 0, the limit from the right of 0, and the limit in general at 0. Flynn. Rob Flynn. All right, Miss Imler, what'd you get? And why? And what numbers do they approach? So 1 for which one?
1 for the right-hand limit and negative 1.
Beautiful. Perfect. Interesting graph, absolute value of x over x. Just 1, and it's negative 1. We're approaching negative 1 from the left. We're approaching 1 from the right. Awesome. Well, those are just simple equations. Sometimes we can combine equations together to make a piecewise function. Okay? So here's an example. You got 2 of these and then you're done. This function is defined by 3 minus x when our inputs x are less than 2. And this function is defined by x squared minus 6 when our inputs are 2 and greater. And the question is to find the limit as x approaches 2. And we might as well find the one-sided limits as well. Well, find the one-sided limits and then tell me what the limit is. Easiest way to do something like this is to not plug it into your calculator. It'll take too long. All right. So don't try to plug it in. I don't know how to plug it in with these constraints. Instead, just sketch it yourself. You pick a couple input. You make sure you're plugging it into the right piece, and then you plot the outputs. So let's see. Start at 0. We're focusing on 2, so I'm going to start to the left of 2, and then I'm going to go past 2. So I'll probably go from 0 to like 4. Let me change that up a little bit. One, 2, 3, 4. Okay. So at 0, which piece defines my input of 0? Miss Bonky. Which piece defines my function when my input, my x, is 0? Top guy or the bottom guy? So the bottom is only used when x's are bigger than or equal to 2. So I'm not going to use the bottom piece, the top one. And what is going to be my output when my input is 0? When my x is 0, what is my y, or my function value? So, yep, 3 minus 0, which is 3. If I use 1, Miss Dawes, what is going to be my output? Yeah, is that Dawes? Are you Dawes? Dawson, okay, that was you. 2, good. I'm going to use the top piece. Now, for 2, Mr. Beard, this top piece, if I plug in 2, I get 1. Should I put a closed circle at 1, or should I put an open circle at 1? Open circle, perfect. Okay, so this is the sketch of my first piece. Now I'm going to sketch my second piece starting at 2. I will have a closed circle. 2 squared is 4. 4 minus 6 is -2. So 2, -2 is where I start my second piece. I go to 3. 3 squared is 9. 9 minus 6 is 3. 3, 3. And it's an x squared, so it's a parabola, so it's going to kind of continue to increase from there. All right, answer those 3 questions. What's the limit as x approaches 2 from the left? As x approaches 2 from the right? And what is the limit in general as x approaches 2? Miss Bergenet for the win. Yep.
Okay, or when it approaches 2 from the left, I got 1.
Yep.
When it approaches 2 from the right, I got -2.
Yep.
And then,
Perfect. It would only exist if this piece and this piece met up with each other and connected. In this case, it does not. Cool? That's piecewise functions. You'll have a couple problems like that on your homework. That's all I got. You may start your homework. I'll put it up on the board.